This presentation is delivered by the Stanford Center for Professional Development.
All right, so today I have two things in mind today. I want to wrap up our discussion of some of the theoretical aspects of Fourier series. We're skimming the surface on this a little bit, and it really kind of kills me because it's such wonderful material and it really is important in its own way. But as I've said before, and now you'll hear me say again, the subject is so rich and so diverse that sometimes you just have to, you can't go into any, if you went into any one topic, we could easily spend most of the quarter on it, and it would be worthwhile, but that would mean we wouldn't do other things which are equally worthwhile, and so it's always a constant trade-off. It's always a question of which choices to make. So again, there are more details in the notes than I've been able to do in class, and we'll be able to do on class, but I do want to say a few more things about it today. That's one thing. Then the second thing is I want to talk about an application to heat flow. That's a very important application, historically certainly, and it also points the way to other things that we'll have a chance to talk, we will be talking about quite a bit as the course progresses. All right, so let me wrap up, again, some of the sort of theoretical sides of things. And I'll remind you what the issue is that we're studying. So this is sort of Fourier series fini. All right? Last time we talked about the problem in trying to make sense out of infinite sums, infinite Fourier series. And the important thing to realize is that that's not by no means the exception. All right? We want to make sense of infinite sums of complex exponentials, sum from k equals minus infinity to infinity, ck e to the 2 pi I kt. I'm thinking of these things as the Fourier coefficients, but the problem is general. How do you make sense of such an infinite sum? And the tricky thing about it is that if you think in terms of sines and cosines, these functions are oscillating. All right, everything here in sight is a complex number, and complex functions. But think in terms of the real functions, sines and cosines, where they're oscillating between positive and negative. So for this thing to converge, there's got to be some sort of conspiracy of cancellations that's making it work. Of course, the size of the coefficients is going to play a role, as it always does when you study issues of convergence. But it's more than that because the function is bopping around from positive to negative, say. All right, and that makes it that makes it trickier to do. It makes it trickier to study. And again, realize that this is by no means the exception. So in particular, if f of t, again, is periodic, of period 1, we want to write with some confidence that it's equal to its Fourier series. We want to write with some confidence, at least we want to know what we're talking about, that f of t, say, is equal to its Fourier series going from k from minus infinity to infinity f hat of k e to the 2 pi I kt. And again, it's really if you want to deal with any degree of generality, it's going to be the rule rather than the exception that you'll have an infinite sum, because any small lack of smoothness in the function or in any of its derivatives is going to force an infinite number of terms. A finite number of terms, a finite trigonometric sum will be infinitely smooth. All the function and all its derivatives will be infinitely differentiable. So if there's any discontinuity in any derivative, you can't have a finite sum. So any lack of smoothness forces an infinite sum. Again, so it's not, because the method is trumpeted as being so general, you have to face the fact that you're dealing with an infinite number of terms here. All right? Now, by the way, I don't mean to say that all the terms are necessarily non-zero, that all the coefficients are necessarily non-zero. That's not true. Some of the terms may be zero. For example, when you have certain symmetries, the even coefficients may be 0, or the odd coefficients may be 0 in special cases, or a finite number of may be 0, or a block of them may be 0. You don't know exactly what's going to happen. But all I'm saying is that you can't resort to only a finite sum if there's any lack of smoothness in there. All right, so again, that's the issue. Yeah? That's f hat of k. That actually is a k, although it looks like a t. That's f hat of k. All right, the kth Fourier coefficient. Now, I'll remind you what the definition is, since we're going to use that. So f hat of k is the integral, as a k, the integral from 0 to 1 of e to the minus 2 pi I kt f of t dt. Is somebody's phone ringing? All right, now, so last time we dealt with, at least in statement, the cases when the function was smooth and is smooth, and you get all that nice sort of convergence that you want. All right, so if f of t is continuous, if f of t is continuous, smooth, or even if you have a jump continuity, then you get the sort of kind of convergence you want. You get satisfactory convergence. I'll just leave it at that because the precise statement we talked about last time, and it's also in the notes. You get satisfactory convergence results. So that's fine. So again, that gives you a certain amount of confidence. You can write this series down, you can manipulate it, you can plug into it and things like that, and nothing terrible is going to happen. But to deal with the more general functions, the more general signals that arise, it really requires a different point of view. All right? Greater generality requires a different point of view, and that's where we finished up last time. Now, it turns out it's not just for fun, even for mathematical fun. That is, this point of view turns out to have far-reaching consequences and really does frame a lot of the understanding and discussion, not only for Fourier series, but in other subjects that are very similar and also in sort of everyday use in a lot of fields of signal processing. So greater generality requires a different point of view. Different terminology, different language, and a whole sort of reorientation. All right, and again, I set that up last time. So let me remind you where we finished up, and I want to put in one more important aspect of it today, and then that's all we're going to do. Sad to say. All right. So again, the condition is on integrability of all things. Instead of smoothness, instead of differentiability, the condition that turns out to be important is integrability of the function. All right. The important condition, and a relatively easy one to verify, integrability. All right. So you say that a function, say that f of t is square integrable, or briefly, you say that f is in L2 of the interval from 0 to 1. I'm only working on the interval from 0 to 1 here, and L2 stands for square integral. The 2 stands for square, and the L stands for Lebesgue, and I'll say a little bit more about that in just a second. If the integral is finite, the integral of the square is finite, f of t squared dt is less than infinity. I want to allow complex valued functions here, although many of the applications are real, but I want to allow complex valued functions, so I put the absolute value of f of t squared there. All right? That's an easy condition to satisfy. Physically, one encounters this condition in the context of this integral representing energy, and so one also says that this function has finite, the signal has finite energy. That's another way of saying it, and you'll see that terminology. All right? So if you have a periodic function which is integrable, like so, all right, so again, if f of t is periodic and square integrable, then you form the Fourier coefficients, and they exist actually. The square integrability is enough to imply that the Fourier coefficients exist. Then you form f hat of k, as before, e to the minus 2 pi I kt f of t dt. And the sum converges, the infinite Fourier series is equal to the function in the sense of mean square convergence. And you have, and this is the fundamental result, that the integral from 0 to 1 of the difference between the function and a finite approximation of the function the square of the difference, the integral of the square of the difference, this tends to 0 as n tends to infinity. Takes up the entire board, and it deserves to. All right, it's an important result. Okay? Okay, now I really feel like I have to say even a little bit more here, but only a little bit more. The fact is, you only get these wonderful convergence results if you not only generalize your point of view toward convergence, but you also have to generalize the integral. All right? This actually only holds for this, the whole circle of ideas really only holds for a generalization of the Riemann integral. Do you have to worry about this? No. All right? But the fact is, you only get these convergence results, such convergence results. You can only really prove them in the context, in a slightly more general context of integration. Convergence results. If you use a different, if you use a generalization of the integral, generalization of the integral even, which is a whole other subject, due to Lebesgue, and that's what the L stands for in L2, due to Lebesgue. He's a French mathematician around the turn of the 20th century who actually, in the context of these sorts of applications, trying to extend integration, trying to extend limiting processes to more general circumstances where they couldn't prove the results classically. Mathematicians were worried about this. He had a more general definition of the integral. And with that more general, more flexible definition of the integral, the limiting processes are easier to handle. You can do more that you'd like to do, but somehow don't feel justified in doing. And in that context, this is something you don't have to know about, all right? But he generalized the integral only. And by doing so, it was perfectly suited to study these sorts of problems. It's really, I mean, it's quite a compelling case. It's a really beautiful theory, but, you know, there's a famous quote of the usual integral that you studied when you studied integrals in calculus is called the Riemann integral. All right, and that suffices for just about every application, but there are more general integrals. On the other hand, John Tukey, who was a famous applied mathematician, was quoted as saying, "I certainly don't want to fly in an airplane whose design depended on whether a function is Riemann integrable or Lebesgue integrable." I mean, it's not, that's not the point. All right, the point really is a theoretical one, not a practical one. But nevertheless, somehow honesty compels me to say what's involved here. All right, so it's in that sense that you have to talk about convergence, and it's not an unreasonable condition. All right, that is, it's also called, as I said last time, convergence in energy, convergence in the mean, or mean square convergence. And what it means is that on average, this sum is converging to the function. On average, being the sense that if you look at the difference between the function and a finite approximation, square that, integrate it, and integrating is sort of taking an average, then that tends to 0 and tends to infinity. It's approximating it over the entire interval on average, rather than concentrating its efforts at approximating it at a single point. And again, you will, if you look at the literature, and I'm talking about the engineering literature, you'll see these terms all the time. You'll see L2 all the time. As a matter of fact, actually, if you take, some of you have probably had courses in quantum mechanics, and if you take it all, sort of an advanced course in quantum mechanics, not that I ever have, but if you do, it's also framed very much in the context of L2 Hilbert spaces and things like that, Hilbert spaces and L2 spaces and so on. I mean, it's not, I'm not making this up. I mean, it really is, it has become the sort of framework for a lot of the discussion. If you want to be sure that you have some certain amount of confidence in applying the mathematical formulas, you need the right kind of general framework to put them in, and this is, for many problems, exactly that. Now, there is one further aspect of it, and that's as far as I'm going to go, that brings back that fundamental property of the complex exponentials that we used when we originally solved for the Fourier coefficients. So I want to highlight that now. So remember, in solving for the Fourier coefficients, way back when, I mentioned this last time, and I want to bring it back now in a more general context again. In solving for the Fourier coefficients, we used a simple integration fact, but it was absolutely everything. It was essential. That e to the 2 pi I nt times e to the minus 2 pi I mt dt, so that we can combine those complex exponentials. That's e to the 2 pi I n minus m t was equal to 0 if m is different from n. If m is equal to n, then it's equal to 1. All right? That simple fact, that simple calculus fact, emerges, it turns out to be the cornerstone for understanding these spaces of square integral function, for introducing geometry into those spaces. So this simple observation, simple fact, is the cornerstone for introducing, if I can say it that way, introducing geometry. I'll put it in quotes because it's geometry like you don't usually think of geometry, but the features are there by analogy. Geometry into this space, into square integrable functions, L2, 0, 1. And when I say introduce geometry, again, I'm reasoning by analogy here, although it's a very powerful analogy. And the thing that makes geometry geometry, as far as Euclid is concerned, is the notion of perpendicularity. All right, that's one of the most important notions of geometry. And that's exactly what gets carried over here. All right, it allows one to define orthogonality or perpendicularity. Same word, same thing. All right, via the inner product or dot product. All right, so let me give you the definition. I'm not going to justify it. There's a justification in the book, actually, in the notes. But it looks like this. So again, if f and g are square integrable functions, and I'm going to assume they're complex. There's a little distinction here between what happens in the real case and what happens in the complex case. Square integrable on 0, 1, as always. That's the basic assumption we make. Then you define their inner product, which is a generalization of the usual dot product for vectors. So a generalization of the dot product for vectors. By an integral formula, right? It's defined by FG, and you write it usually, there are various notations for it, but a common notation is just to put them in a pair. Or sometimes people write it with an angle brackets, or sometimes people do all sorts of things. Sometimes physicists call it, bra vectors and ket vectors and, all sorts of bizarre, unnatural things. But I'll take the simplest notation. So it's the integral from 0 to 1, f of t times g of t bar complex conjugate dt. That's because I'm allowing complex valued functions. If g of t were a real valued function, then I would just have integral of f times g. But because it's complex for reasons which, again, are explained a little bit more in the notes, you put the complex conjugate in there. Now, what you have to believe is that this is sort of the continuous infinite dimensional generalization of the dot product of two vectors. How do you take the dot product of two vectors? You multiply the components together, the corresponding components together, and add. All right? So it's like you're multiplying the values together, although the function times the conjugate of the other function, those are the values, and you're adding, but continuously in the sense of taking the integral instead of the sum. All right? That's sort of where it comes from. Now that's fine, but the real benefit is it allows you to define, if you ever want to do that, when two vectors, when two functions are perpendicular. So you say that f and g are orthogonal. You could say they're perpendicular, but it sounds ever so more mathematical if you say they're orthogonal. All right? Orthogonal, and if you write it neatly, orthogonal, much neater. If their inner product is 0, if fg is equal to 0. Period. That's a definition, all right? That's a definition. Now, where does the definition come from? Again, because I can't say everything as much as I'd like to, let me refer to the notes because it's actually not so unreasonable. This definition comes from exactly wanting to satisfy the Pythagorean theorem for inner products. Now, the calculation we did with the complex exponentials shows exactly that different complex exponentials are orthogonal. One more thing, actually. Let me introduce the length of a function, or the norm of a function, in terms of the inner product, or in terms of the integral, same thing. So the norm of f The norm of a function f is defined by, well, the square of the norm is just the inner product of the function with itself, just like the square of the length of a vector is the inner product of a vector with itself. So the inner product of f with itself is the norm of f squared, and that's the notation you use. And so what is that? That's exactly, so the norm of f squared is exactly the integral from 0 to 1 of f of t squared dt. And let me just tell you what the Pythagorean theorem is then. All right, the Pythagorean theorem is, I'll do it over here, because that's where this comes from. That's exactly where this definition comes from, and that's exactly where the property comes from. The Pythagorean theorem is exactly this, that f is orthogonal to g if and only if the norm of f plus g squared is equal to the norm of f squared plus the norm of g squared. And that is if and only if the inner product is 0. Why is that the Pythagorean theorem? Because of vector addition. Right? If I wrote vectors u and v, then this is the vector u plus v, right? If I just write vectors. And the Pythagorean theorem says the square of the hypotenuse is the sum of the squares of the sides for a right triangle, and only for a right triangle. That characterizes a right triangle. All right? So that says the norm of u plus v squared, the square of the length of the hypotenuse is the sum of the squares of the other two sides, u squared plus v squared. And that holds only exactly when the two vectors are perpendicular. And that's where the definition of the inner product comes from and everything else. Beautiful. It's beautiful. All right? So the trick is in extending that from, it's beautiful if you like this sort of thing. The trick is extending that from vectors to functions and reasoning by analogy. All right? It's not, you know, so, all right, so now let me say what you should think about and what you shouldn't think about. The analogy is very strong. In many ways, your geometric intuition for what happens for vectors you can draw carries over, at least algebraically, to this more general situation. However, all right, so let me say one more thing then. These complex exponentials are exactly functions, are orthogonal functions of length 1. That calculation that I've just erased with complex exponentials says this. It says e to the 2 pi I nt, inner product with e to the 2 pi I mt. All right? That's the integral of this times the conjugate of this. The conjugate of e to the 2 pi I mt is e to the minus 2 pi I mt. That's where the minus sign comes from. All right? This is equal to 0 if m is different from n, and it's equal to 1 if m is equal to n. All right? These are orthonormal vectors with respect to this inner product. They are orthogonal. Their inner product is 0 when they're distinct, and they have length 1. Their norm is equal to 1 when they're equal. Okay, now, as I said, you reason by analogy. You can visualize what it means for vectors to be perpendicular. You can draw this picture. All right? So you might say to yourself, I should be able to visualize this. I should be able to sit in a quiet room, turn the lights off, and visualize what it means for complex exponentials to be orthogonal. Yes, yes, I see it. No, you don't. Let me relieve you of this burden. There is no reason in hell that you should be able to visualize when two functions, let alone complex exponentials, are orthogonal. Don't beat yourself up trying to do that. And don't say to yourself, you're less of a person if you cannot visualize when two functions are perpendicular. Not only complex exponentials, but sines and cosines, you know, all sorts of innocent-looking functions out there that you have worked with for all of your life turn out to have this sort of orthogonality relationship. But you might say to yourself, like sines and cosines. So sine of t is orthogonal to cosine of t. You know, or sine of 2 pi t is orthogonal to cosine 2 pi t. You know, all sorts of interesting results like that. But you might say to yourself, gee, if I look at the graph, I should be able to visualize this. Don't bother. All right? There's no point. There's no point. It's reasoning by analogy. All right? The fact is you establish these formulas, you establish they're orthogonal, and then you apply your intuition for orthogonal functions, for orthogonal vectors where you can visualize it to situations where you can't visualize it. All right? And that's the real power of this line of reasoning, because you can apply your intuition to places where it should have no business applying somehow. All right? All right, now, almost. Almost. The final thing then, the final piece of this approach to Fourier series is to realize that the Fourier coefficients are projections of the function onto these complex exponentials. All right? So again, I want to remind you of one of the ways you use inner product is to define projections, to define orthogonal projections in particular. So you use the inner product for vectors to define and compute projections. All right? If u and v are two vectors, unit vectors, say norm of u equals 1 and norm of v equals 1, then what is the projection of v onto u? And the projection of v onto u is just the inner product of v dot u. That's how much u knows v, or v knows u. All right? The projection here is the inner product of v with u. Okay? And how much does u know v? It's the inner product of u with the same thing. All right? So the vector that the vector projection here is, that's the length of the projection. All right? Then the vector that goes in the direction of u that has this length is this times, so the vector projection is inner product of v with u times u. All right? U is a unit vector, so you go in that direction, this length, and that's how you project. And it shouldn't be shocking. It should be somewhere in your background to realize, certainly if you had classes in linear algebra, that decomposing a vector into its projections onto given vectors can be a very useful thing. It's breaking a vector down into its component parts. Breaking a vector down into its component parts. All right? Now, what is the situation for functions? It's exactly analogous. I don't want to say it's exactly the same because you can't draw the picture, but you can write down the formulas, and the formulas are a good guide. The formulas are a good guide. All right, what is the Fourier coefficient? The Fourier coefficient is exactly a projection. All right? The Fourier coefficient, if I compute the inner product of the function f with the complex exponential e to the 2 pi I n t, then that's exactly the integral from 0 to 1 of f of t times e to the 2 pi I n t var dt. That is the integral from 0 to 1 of f of t e to the minus 2 pi I n t dt. That is the nth Fourier coefficient. The nth Fourier coefficient is exactly the projection of the function onto the nth complex exponential. All right? Cool. Way cool. Infinitely cool. So cool. And what is writing the Fourier series? What is writing the Fourier series? To write f of t is equal to the sum from k going from minus infinity to infinity, f hat of k, e to the 2 pi I kt, is to write f of t is the sum from k going from minus infinity to infinity of the inner product of f with the kth complex exponential times that kth complex exponential. This is a number, all right? That's the Fourier coefficient. That's the length of the projection of f onto its kth component. And there's the kth component. All right? It's exactly what that is. And it's this point of view that is so ubiquitous. All right? So ubiquitous. Not only in Fourier series, but in other versions of essentially the same ideas. And you see this all the time in signal processing. I talked about wavelets last time. I mentioned wavelets just very briefly because wavelets is such a hot topic. It's the same sort of thing. you're trying to decompose the function into its simpler components. In this case, the simpler components are e to the 2 pi are the complex exponentials. All right? So to write an expression like this down, to be able to say this in the appropriate notions of convergence, is to say, I'll do it over here, is to say that the complex exponentials form an orthonormal basis for the square integrable functions. Right? To be able to write this statement and understand what it means in terms of convergence and all the rest of that jazz is to say that the complex exponentials, that is all of these, e to the 2 pi I kt, k going from minus infinity to infinity, form an orthonormal basis for these periodic functions, square integrable periodic functions. All right? And then sometimes the game is to take different orthonormal bases. Wavelets are nothing but, or I don't say nothing but because they have their own fascination, they are another orthonormal basis for square integrable functions. The complex exponentials are not the only orthonormal basis. Just like any vector space doesn't have just, has lots of different orthonormal bases. These are particularly useful ones. So to write this synthesis formula is to express f in terms of its components. What components? The components in terms of these elementary building blocks. All right? And what are the coefficients? The coefficients, like they are for any orthonormal basis, are the projection of the vector in those directions. All right? It's very satisfying. And you should try to put this in your head. Yeah?
In the sense that you can't get one from the other by like a little rotation, like you think of vector.
Well, it's more complicated. So the question is, are the bases, like in finite dimensional spaces, the bases are related to each other by essentially a rotation, a unitary or orthogonal matrix. And in space, yes, you have unitary transformations, linear operators that are unitary, but the definitions are a little bit more complicated. But you have similar sorts of things. All right, you can get from one orthonormal basis to another orthonormal basis. Okay. All right. This is, like I say, so one can, of course, say much more about this. I don't want to. All right. Well, I do want to, but I can't. All right. But it's this point of view that is important for you to carry forward. All right. That's all I'm saying, because you will see it. You will see it. All right. And again, the idea is you reason by analogy. All right. It's hard to write down this formula. All right. That's something new. All right, writing down a formula, writing down an inner product in terms of an integral. All right, okay, I got to deal with that. That's something hard, and I can't visualize it. All right, but the words you use in the case where you can visualize things are almost identical to the words you use in the situation where you can't visualize things. All right, and you can carry that intuition over from the one case to the other case, and it's extremely important. And I'll give you I keep saying one final thing. So this time for sure, an application of this is what's so-called Rayleigh's identity, which is nothing more than to say a length of a vector can be obtained in terms of the sum of the squares of its components. All right? You know how to find the length of a vector in Rn. You add up the sum of the squares of the components. All right? You do the same thing here. Rayleigh's identity and I will not derive it for you, but it is derived in the book, and I even say something like, do not go to bed until you understand, do not go to sleep until you understand every step in the derivation. It says the integral from 0 to 1 of f of t squared dt, you write it in terms of its Fourier coefficients, I didn't write that down, is the sum of the squares of the Fourier coefficients. K going from minus infinity to infinity of f hat of k squared. All right? That's Rayleigh's identity. It says the length of a vector is the sum of the squares of its components. All right? The components of the function are its Fourier coefficients. All right? This is the length of a function. It is the inner product of or the square of the length of a function. It's the inner product of the function with itself. It is the sum of the squares of its components. That's all this says. And it follows algebraically exactly in the same way as you would prove this using inner products for vectors. Exactly. Exactly. All right, now, this was known before any of this stuff was put in place. All right, but when all this, that is this sort of general framework was put in, this identity was known before the general framework of orthogonal functions, square integrable functions, all the rest of that jazz. And it was viewed as an identity for energy. All right, this is the energy of the function, and these are somehow, you know, the individual components here. And that's why one often says you can compute the energy in the time domain or the frequency domain. We're going to find an analogy for this for Fourier transforms. All right, but it really says nothing other than the length of the vectors is the sum of the squares of the components. How much? So again, let me write down. Here's f of t is the sum of. Here's this Fourier series. F hat of k e to the 2 pi I kt. All right. All right. How much energy does F have as a signal? It has this much. All right. How much energy does each one of its components have? Well, the energy of each one of the complex exponentials is 1, because they are of length 1. All right. So how much square energy does each one of the components have? It's the magnitude of this thing squared. It's the multiplier. It's the projection out front. F hat of k squared times the energy, which is 1 of the complex exponential. So what is the total energy here? What is the square of the total energy here? It's the sum of the squares of the contributions of the energy from the individual components. Each individual component is contributing an amount F hat of k to the whole sum. Or the energy it contributes is the square F hat of k, absolute value squared, to the whole sum, to the whole amount. Okay? Pretty cool. Pretty cool. All right. Here ends the sermon. Don't leave without putting something in the collection plate. Oh, all right. All right. Here ends the sermon on inner product, square integrability, and so on. Okay? I say, all I can say is, trust me, you'll run into it again. Now I want to do, and I probably won't finish it today, I'll finish it up on Wednesday, although it goes pretty fast. I want to do a classic application of Fourier series to the study of a classic physical problem. Matter of fact, the problem that launched the whole subject. So I want to do an application to heat flow. All right. Now, this is a very important part of your intellectual heritage. All right, I'm serious. That is, if you're going to be practicing scientists and engineers, you know, you want to know something about where the subject came from, because again, you know, you somehow wind up revisiting a lot of these ideas in different contexts, but often in similar contexts. And this was the problem that really started it all. This was the problem in studying how the temperature varies in time when there's some initial temperature distribution. All right, so you have a region in space and with an initial temperature distribution and an initial distribution f of x of temperature. I say f of x here just to indicate that x is some sort of spatial variable. All right, so some region in space. You know, the dimension of x is the dimension of the region, all right? And the question is, how does the temperature, so then heat flows, all right? So you have initial distribution of temperature, that's what happens at t equals 0. Then as t increases, the temperature changes, all right? The heat flows from one part of the body to the other part to another part of the body, and you want to know, how is that governed, all right? How does the temperature change both in position, I should say vary, well, change is fine. How does the temperature change in position and time? All right, this was an important problem, still is an important problem actually. And we're only going to handle one very special case of it, a case, the original case that was handled by Fourier series, that's the problem that Fourier studied. Where periodicity comes into the problem naturally because of periodicity in space. So to study this problem means to say, first of all, what the region is, and then to say what the initial temperature of what the initial distribution of temperature is, or at least say that there is given an initial distribution of temperature. All right. So we look at a heated ring. That sound. Okay. All right. Something like this. All right. Given an initial temperature, given with an initial temperature, say, f of x. f of x. X is a position on the circle. X is a point on the circle. Okay? And we let u of xt be the temperature at x at time t, at position x at time t. All right, and the question is, can we say something about it? That's the function we want to find. We want to study u of xt. All right, now, the fact is, periodicity enters naturally into this problem, periodicity in space. Because the circle, the temperature here is the same as the temperature at the same place. As if I increase it by 2 pi, if I'm going around a circle, then obviously the temperature is periodic as a function of position. Okay? So the temperature is periodic as a function of x. All right, and let's normalize things so we assume the period is 1. So the circle is radius, whatever it is. Or another way of looking at it is imagine the circle is just the interval from 0 to 1, and I identify the endpoints. All right? So let's suppose we have period, just because we've been dealing with functions of period 1, let's suppose that. Let's suppose period 1. Period 1. All right, so that is the function, the initial temperature distribution, f of x plus 1 is periodic of period 1. And so is u in x, not in t. It's not periodic as a function of time, but it's periodic as a function of the spatial variable. U of x plus 1 for any value of t is the same thing as u of x at that value of t. Okay? That's fundamental. And that's how Fourier got into this. That's how he introduces, that's why he introduced those ideas. He considered this problem where there's periodicity in space. There's the symmetry of the object that you're heating up, and that has consequences. All right. So now, with a certain amount of confidence, with a certain amount of bravado, we write down the Fourier series. So we write the Fourier series u of xt is the sum from k going from minus infinity to infinity of c sub k. I'll write it like this: c sub k e to the 2 pi I k x. It's periodic in the spatial variable, so the variable in the complex exponential is x. Where is the time dependence? No, the time dependence is in the coefficient c. That's where the time dependence has to be. All right, k is just a constant, or k is just an integer. The time dependence is in the ck. That is a better way, more accurate way of writing it, is like so. U of xt U of xt is the sum from k going from minus infinity to infinity of c sub k of t. I know what it is, the Fourier coefficient. I'll bring that in later, but let me just write it in terms, let me just call it c right now. C sub k of t times e to the 2 pi I k x. All right, periodic in x, varying in t. How does it vary in t? That's what we want to know. All right, the mystery here are the coefficients. We could solve the problem if I could find the coefficients somehow in terms of the initial temperature distribution. So what are the ck? That's the question. All right, now, we're going to be able to attack this problem because, independent of periodicity, independent of anything else, heat flow is governed by a partial differential equation. All right, the flow of heat on a circle or another region is, and this is in itself a big subject, but it's one of the basic equations, partial differential equations of mathematical physics, which you have probably seen somewhere in your life. And again, you will see again, heat flow, I'll just do it in one dimension, all right? I'm talking about one-dimensional problems here, but there are also ways of analyzing this for flow over a two-dimensional region or a three-dimensional region. We have the heat equation, which says that the time derivative of the temperature is proportional, is some kind, maybe I should call it another constant because I've already used k, a, times the second x derivative. All right, that's the one-dimensional heat equation. All right? I'm not going to derive that. Actually, I have a derivation of that in the book that sort of follows Bracewell's discussion of the heat equation. But that's a fundamental equation of mathematical physics. The constant A here depends on the physical, because this is one of these great dodges of all time. The constant A depends on the physical characteristics of the region, which no one wants to talk much about. But that affects the size of A. All right? I should say more generally, this equation governs not just the flow of heat, but it's in general, it's called the diffusion equation. It governs how things diffuse. What things? Like charge through a wire is studied by this equation. Holes through a semiconductor are governed by an equation like this, a higher dimensional version of the equation, but the same idea. All right, so this in general governs, this is also called the diffusion equation, and it governs phenomena that are associated with diffusion. It's a general term, but it's a term that you've probably run across. All right. Now, I want to choose. I'm not going to get too far today, but I'm going to get a little along the way. So I want to choose. I want to apply this equation to study this function. All right. So I want to use this for the ring. All right. And just to simplify my calculation, although it does not make any substantive difference, I'm going to choose the constant so that A is equal to 1/2. That's a standard choice, certainly for the mathematical analysis, but it doesn't matter. You could have the constant tagging along in the whole thing. It wouldn't affect any of the analysis. So I'm going to choose A equals 1/2, or choose constant so that A equals 1/2. So the equation looks like U sub t is equal to 1/2 U sub xx. All right? Now, I'm going to shortcut the discussion a little bit. There's one way of doing it in the book, in the notes, which is a little bit more rigorous than what I'm going to do, although both can be justified very easily. I'm going to plug that equation, that formula for you. We have a formula for you, in some sense. Not in some sense. We have a formula for you, in this sense. And I'm going to plug this into the equation. Plug U of xt is sum over k, ck of t, e to the 2 pi I kx into the equation, into U sub t is equal to 1/2 U xx. What happens? What happens? Well, so U sub t, if I differentiate with respect to that's indicating the partial. I'm sorry, I should have said this, but I assumed everybody knew. U sub t is the partial derivative with respect to t of that function over there. So what is that? Well, the only thing that depends on t here are the coefficients c sub k. So that is sum over k, ck prime of t times the complex exponential. That stays alone, 2 pi I k x. What is uxx of this expression? Well, here I put the derivatives on the complex exponential, and I differentiate twice. Differentiating complex exponential, just like differentiating an ordinary exponential, the constant here comes down if I differentiate. So I get ck of t. That's left alone because I'm differentiating with respect to x. And then if I differentiate e to the 2 pi I kx twice with respect to x, I get 2 pi I k squared times e to the 2 pi I kx. Nothing up my sleeve. No tricks. No deceptions. Okay? So that's, to carry this out one more step, that's the sum over k, c sub k of t times minus 4 pi squared k squared, because I squared is minus 1, times the complex exponential, e to the 2 pi I kx. All right? Now equate the two. Equate the two. Then we got to go. Damn. Equate the two sides. Use the heat equation. Plug into the heat equation. So I get sum, plug into ut is equal to 1/2 uxx. Then I get sum over k, ck prime of t, e to the 2 pi I kx is equal to 1/2 times that thing, so it's going to be sum over k minus 2 pi squared k squared times c 2 pi squared k squared times ck of t times the complex exponential, e to the 2 pi I kx. Right, not hard. That's not a hard step. Okay? All right. Now what do? You equate like terms. Equate the coefficients. If I equate the coefficients, something great happens, whose full consequences I'll do next time. If I equate the coefficients, I get ck prime of t is equal to the coefficient. When I say equate coefficients, I mean the coefficients of the complex exponential. Ck prime e to the 2 pi I kx. What's the corresponding coefficient over here? It's this, is equal to minus 2 pi squared k squared ck of t. But my friends, you know, that is a simple equation. That is an ordinary differential equation for ck. Right? I can solve this. Pas de problème. I get ck of t is ck of 0, the initial condition, times e to the minus 2 pi squared k squared t. Formidable. All right? I've found my coefficients. Pretty cool. All right? Extremely cool. Très cool. You know? And next time, what I haven't done is I haven't brought back in the initial distribution of temperature, and I want to manipulate this solution a little bit more, and something absolutely magical happens. Wait for it on Wednesday. Okay.
So when you put the coefficients,